have here the purpose to present of our integrated group project from Group 4A. Our topic is combined gas steam power cycle. So here goes our group members.
So I am Exxon Rogério Monique. My ID number is 20,980.
So I am Devon. My ID is 200000053.
I am Achola Book. My ID is 20,146.
And I'm Ibrahim Mohammed. My ID is 2017.
Okay, now let's see the chapter 1, which is the introduction and background of our IDP project. So what is basically IDP project? It's an extensive overview of the actual work of chemical engineers for chemical engineering students' life. Okay, the goal of our IDP project is to combine gas steam power cycle is to the power the new LPCP. So our team choose water as a cooling medium in the heat exchanger, and calculations are used to obtain data to determine the amount of coal required for the heating furnace per second, steam produced and power actually produced, and supporting equipment use. So by chemical engineering thermodynamics, one part of the project taught us to determine the overall efficiency and backwork ratio of the combined power plant, and the process heat transfer taught us to design shell and tube heat exchangers. Now I pass to Ibrahim for part 2.
Okay, thank you, Devon. So now I'm going to introduce you about chapter 2, which is the about chemical engineering thermodynamics. Let's start. There is a combined gas steam power cycle was designed. Then the steam cycle consists of one pump, two steam turbines, two generators, and one condenser, whereas the gas cycle consists of a compressor, two gas turbines, two generators, and one combustion chamber. These two cycles are combined and a single heat exchanger is used. Then the fluid of the steam power cycle is water. Where it's heated, it turns into the steam and spins to drive a steam, a turbine which drive an electrical generator. A fast spinning turbine drive a generator, then converts part of the terrestrial energy, rotational energy into electrical energy, and then it can use to power the new Lamut naval base and its city. Then the coal is needed in the gas power cycle to provide power to run the steam smoothly. Our task is determine the efficiency, then the backwork ratio, then amount of coal required and amount of steam produced, then the actual power produced, and the number of equipment required to operate the gas steam combined power cycle. Then the problem statement pointed out that the goal of the power plant is to generate 500 megawatts, which is the input steam temperature and pressure reaching around 700 Celsius and 30 megapixel respectively. Lastly, that gives the power that the steam turbine needs to generate as 500 megawatts. Now I'm going to turn to Achol.
Okay, so I'm going to explain about the process heat transfer part. So first we were asked to design a heat exchanger. So we are going to use the log mean method to determine to select a heat exchanger that will meet the required power heat transfer requirement. So first of all, we had to decide the type of heat exchanger that we use suitable for the application. And then we had to determine the unknown inlet and outlet temperatures, of which for our case, for the project, we were already given the outlet temperature for the hot stream at 700 degrees Celsius. And then we found the outlet temperature from the thermodynamics as 45.8 degrees Celsius. And for the cold stream, we assume both values for the inlet and outlet as 10 and 200. This makes sense and is relevant because the cold stream is from a high temperature, from a low temperature of 10 to 200 degrees Celsius, which means it's being heated. So the heat that is lost from the hot stream from 700 to 45.8 degrees Celsius is used to heat the cold stream. So our assumption is much relevant for calculations. Next, we had to calculate the log mean temperature difference and the correction factor. So we calculated the log mean temperature difference and we got it as 176.06 degrees Celsius. And we calculated the correction factor for the condenser and we got it as 1. This makes sense as when it's from the references when Googled, it gives a correction factor of 1. And then next we had to calculate the surface area from the equation of QL is equals to UAS correction factor times delta T log mean, and of which we got the U, the value of the overall heat transfer coefficient. We assumed it to be 1,800, which is relevant from the values given in the table. I found my surface area to be 182.89 meters squared, of which we assumed the number of tubes to be 3,000 from the reference range, and we finally got the length to be 1.29 meters. And so things that we maintained, things such as the mass flow rate, and also the condenser is expected to function at a constant flow rate with no variation in time. That's why we maintain the mass flow rate. So that's it from my part.
So in conclusion, this combined gas steam power plant design met the requirements indicated in the integrated project issue statement. In the combined gas steam power plant, this quantity of power is generated by using one gas compressor, one gas boiler, two gas turbines, one steam power turbine, two generator, one heat exchanger, one condenser, and one pump. This plant's overall efficiency and backward ratio are 90% and 37% respectively as needed in the question. And the final design of the condenser meets all the specifications stipulated in the problem statement of the integrated project. We know that fouling plays significant roles in reducing the performance of the heat exchanger. So there are few methods that can be implemented to enhance the maintenance, the efficiency of the heat exchanger, such as the periodic cleaning, periodic maintenance, the fouling factor that will increment the flow rate, that will increment in the flow rate, increase the velocity of the fluid. Thus, the turbulent flow will increase, therefore the fouling tendency can be indirect. So by this way, we close our presentation.